We now have a speaker online, and I'm looking at the technical stuff to see whether they have Aimee Slangen online. Dr. Aimee Slangen is an oceanographer. Oh, there she is. Yeah, we can see you now. I don't know whether you can see us. Dr. Aimee Slangen is talking to us about the IPCC. She's not only a well-known oceanographer in the Netherlands, she also contributed to the panel for the international panel for climate change, the Intergovernmental Panel for Climate Change. And she will talk to you about climate change scenarios. Can everyone be silent here so we can all hear Aimee when she speaks? Thank you. Aimee, the floor is yours.
Thank you very much. And thank you very much for inviting me to speak today. I'll wait for my presentation to come up. And so far, my compliment for the organization. It's been really nice to follow this seminar online as well. So very well done. Yeah, great. So now I can see the presentation and myself. That's good. I hope you can hear me okay as well. It's my honor today to talk to you about global and regional sea level projections from the IPCC 6th Assessment Report. As Dr. Femke just said, I contributed to the latest IPCC report on the chapter on oceans, cryosphere, and sea level change. Yes, let's see if I can change slides. Yes. So I always like to think of sea level change as some kind of a thermometer of climate change. So there's lots of processes involved in sea level change. So it's changes in the ocean, the temperature of the ocean, but also, of course, changes on land, melting of land ice, local vertical land motion, changes in the atmosphere, changes in how much water is stored on land. So it's really bringing together all of these processes. And for me, that's what makes sea level change such an interesting topic, but also I think such a relevant topic. And if we briefly look back at sea level change, if we look at the past 50 years, so since 1970, you can see in this graph on the left, there's a dashed line, that's a thick black line. That's the total observed global mean sea level change. And with the stacked colors, you can see how the ocean in blue, the ocean warming, and the ice sheet mass loss in gray, plus the land water storage change together very well explain the total sea level change that we've observed. So we have a quite good idea of the drivers of sea level change. What you also see in this table on the right is that sea level has been speeding up, sea level rise. So if we look over the entire 20th century, it's about 1.7 millimeters per year. But if we get closer to the present day, and we saw that in presentations earlier today as well on the satellite altimetry, the sea level rise is increasing. And for the latest period, it's about 3.7 millimeters per year. So this is really increasing over time. Now, if we want to model sea level change into the future, unfortunately, it's not that easy. And please don't go and read this entire spaghetti plot. It's really to show that we don't have one model that we can model sea level rise with. We do have climate models that give us parts of the information, but we can't, these climate models cannot model all the changes in, for instance, the land ice. They don't have all the projections for groundwater changes in them. So we really have to combine different kinds of models, and that's what makes it quite challenging to get these sea level projections. We really have to run different kinds of models and then add them together in order to get these total sea level projections. There's been quite a lot of developments in the IPCC reports, and I saw some figures earlier from, I think, the SROC report from 2019. I think the first time we actually had regional sea level projections was in the IPCC 5th assessment report back in 2013. Back then we used CMIP5 climate models and with radiative concentration pathway scenarios. So these are scenarios indicating how much changes there were in the radiative forcing in the atmosphere. So that was the first time we had regional pictures, regional projections of sea level change. Then in SROC, we had some new information on the contribution from Antarctica. So in the SROC report, the AR5 Antarctic estimates were replaced by new Antarctic estimates. And then finally, in the AR6 report, so the latest IPCC report from 2021, we used the latest set of climate models. So that's the CMIP6 climate models. And we used, rather than just the radiative concentration pathways, we used also socioeconomic pathways, the SSP scenario. So that was the combination really of, okay, what is the world going to look like? So really these what if scenarios. What if the world as a whole reduces, goes for a more sustainable way of living, so less greenhouse gas emissions versus, okay, what happens on the other hand if we get way more greenhouse gas emissions than today. And another novelty for this AR6 report was that we used emulators. And this is a fancy methodology of basically linear regression, but then a fancy way of doing that so that you can have a full probability density function rather than relying on just a couple of climate models, because these climate models are really expensive to run. They take a lot of time. And as a result, it's difficult to sample the entire probability space. So we use these emulators to fill up this probability space, and that gives us way more information on the probabilities of different projected changes. Now, on the right, I've plotted graphs of the changes in the global mean contributions to sea level change in the projections. So if you would focus on the black dots on the left of each of the graphs, the RCP 2.6 or the SSP 2.6 scenario, so that's really a scenario in which the carbon emissions are radically reduced. The global mean sea level projections have gone up slightly in this latest IPCC report. And this is mainly due to a higher expected contribution from Antarctica, even under these reduced greenhouse gas emissions. If you then go to the right-hand plot, and again focus on the black bars there, we see that for the highest scenario, the RCP 8.5 or the SSP 5 8.5 scenario, actually the projections have come down a little bit compared to the SROC scenario. And that's because of a combination of different contributions. For instance, the land water contribution being expected to be a little bit lower than it was in the AR5 or in the SROC reports. But overall, you do see that these numbers are not radically changing anymore. So these projected changes under the various greenhouse gas emission scenarios, they stay rather similar. So what does this look like if we actually go and look over time? Well, if you look in the sort of the coming 25 years, so until 2050, we actually see very little difference between the different greenhouse gas emission scenarios. So it doesn't really matter yet what the decisions today will be made, which kind of decisions will be made, so how much greenhouse gas emissions we will have in the next years. Because by 2050, we expect a global mean change of about 20 centimeters. It can be a couple of centimeters less and it can be a couple of centimeters more. It's really further down the line that we will see the effect of decisions made today. So if we go and we follow a Paris Agreement scenario, this is the SSP 119 scenario, you would expect about 40 centimeters on average on a global mean. Whereas if we continue on the present road, this would be closer to about 70 centimeters. And we see this divergence continue further down into the future. So if you go to 2150, it even diverges more. And the effects of these greenhouse gas reductions now become even starker in the far future. And this is also continuing further down the line. So if we look at long-term sea level projections, we see that sea level rise will continue for centuries to millennia. because of all these processes that have been put in motion. So we have an ocean that is currently warming, and it's mainly the top of the ocean that we've seen warming, but that warmth hasn't gone into the deep ocean yet. So that's a process that's still ongoing. This deeper ocean doesn't even know about climate change yet. And the same goes for these Antarctic and parts of the Greenland ice sheet. They respond relatively slowly to temperature changes because they're so big. And some of the sort of a snowflake that falls in the middle of the Antarctic ice sheet will take thousands of years to travel to the side of the ice sheet and finally melt into the ocean. So that snowflake that is currently falling there doesn't even know about climate change yet. So we do know that there is, or we do expect that there's going to be increasing contributions from the ice sheets as well. So that means that sea level will still continue, even if we would stop our greenhouse gas emissions today. The good news is that the speed of this sea level rise does depend on the emissions. So we do see a difference whether we cut the emissions today or whether we continue. So that makes a big difference. But you do see that even in the long term, so until for instance, in 2300, even if the greenhouse gas emissions are reduced, we're still looking at numbers up to about 3 meters of sea level rise. Whereas if the emissions increase even further, those numbers would increase even further as well. And you would have several meters of sea level rise. So thinking about sea level rise, actually, the question is not really if we will reach 0.5 meter or if we will reach 1 meter, but the question is really when. So instead of asking how much sea level rise will we get in the year 2100, so will this be 40 or 50 or 60 centimeters, the question that is probably more relevant to policymakers is when will this 0.5 meter be crossed? Because then you can already start thinking, okay, what do we want to do? What do we need to do to adapt against this 0.5 meter or this 1 meter or this 1.5 meter of sea level rise? So you can have these plans ready. And once we know which scenario we are on, you can start adjusting your adaptation to that. So that's what we try to show by this milestones plot. You can see that actually in all of the scenarios, this 0.5 meter will be crossed roughly before 2150. So you know that this 0.5 meter is going to be crossed some sooner or later, and that hopefully makes it easier as well to start thinking about how to adapt to these changes. So if we think about sea level change, so far I've mainly talked about global sea level change, but actually there's a large spatial differences, and we saw that in the satellite observations as well. You see these big differences. So even if the global mean currently is about 3.5 millimeters per year, there's definitely places where this is more, and there's definitely places where this is less. And the same goes for the future. So here you see the 2100 sea level projections under Paris Agreement scenario on the left and our current pathways on the right. And you do see there's strong regional variations in this. If we would take all the coastal pixels and compute the average of that, we see that about 2/3 of the global coastline will have a projected change that is within 20% of the global mean increase. So it could be 20% more or 20% less, but it's relatively around that global mean. So the global mean is a good first order approximation of the sea level rise, but locally there are definitely differences. To facilitate everyone figure out what is happening at their coast, we made this sea level projection tool between the IPCC and the NASA, where we show these sea level projections that I've just shown. And make them available for everyone to work with them, to play with them, to zoom into your location of interest, and also to replace parts of these projections. If you think, for instance, in the case of vertical land motion, we know that the global vertical land motion estimate is not perfect. So by taking the projections of the IPCC, removing the IPCC vertical land motion, and for instance replacing them by a local information, you would get a better kind of projection. But everyone here can download, you can zoom into your location, and that's what I did here. So if you zoom into the Thailand region, you can also look at the different contributions, and we do see that it really depends on the location and the vertical land motion in that location, what the local total sea level change will be. So if you look at the global mean of about 70 centimeters, so 68 in this case, it really depends on which tide gauge you choose and what the local vertical land motion is there on what the final sea level rise, the final relative sea level rise will be. So this means that local knowledge is really required. And Tijmen, I think, will talk a bit more about this as well later in his presentation. So there's different ways of responding to sea level rise, and in the IPCC we made this overview of different options. And so this is really giving the typical timescale, so how long it takes and how long a measure is valid for or can be used for. So you can think about ecosystem-based adaptation, which can typically be implemented rather quickly, but also is not always working for a really long time. So the timescales are short, but you might need to do it again and again as time progresses. But you can also think about sediment-based protection, so putting sand nourishments in front of the coast for coastal protection. You could think about elevating houses. That takes a bit longer, but might give you a bit longer as well. And then, of course, there's the long-living societal legacy, so the really big impact decisions of building big levees, which take a long time to build, but also give you a longer time to protect, or planning the relocation. And I mean, in the Netherlands, this is a question, and I'm sure in Thailand it's a similar question, is how are we going to deal with this sea level rise, and what's the best way? And I think wherever in the world you are, of course, there's lots of different decisions that need to be made and different options that are available, and really depending on the local situation. So depending on whether you can have a lot of response or not a lot of response, so the risks to a location also increase or decrease, and that's what's shown with these burning embers, so-called burning embers diagrams. So the darker the color, the darker towards the purple, the higher the risk is. And here we put the risk against the sea level rise. So you can see that for higher sea level rise scenarios, the risks are typically larger, but the risks are also larger if no action is taken versus when a lot of action is taken to adapt to the sea level rise. And that depends very strongly on again, where you are in the world, whether you're in a resource-rich coastal city, then it's typically easier to adapt, or than compared to an urban atoll island, for instance, where the risks are way larger, and it's way more difficult to even begin to adapt to these changes. So to sort of wrap up, and I think I'm okay, going for time. So to wrap up, if we think about sea level rise, more warming means more impacts and also more sea level rise. And we know that sea level rise will continue throughout the 21st century and beyond. So it's really not, often 2100 is mentioned as this end number, but it's not like sea level rise will stop there, unfortunately. So we do need to think further as that as well. There are substantial regional differences with a strong dependence on VLM in some places. And in Thailand, this is the case, as we've seen from earlier presentations as well. Yeah, and the risks depend strongly on where you are in the world and on how you respond and what kind of adaptation is taken. And I'd like to finish with showing you this graph from the IPCC synthesis report, which is really showing quite strongly how how warming the planet has there's differences in generations. So the generation of my parents, they've experienced about a degree of warming in their lifetime. The generation of myself will experience maybe 2 degrees in a lifetime, and the generation of my children might experience between 2 and 4 degrees of warming. So that really shows that this climate change is really increasing in speed. And yeah, we need to really think about the future. Thank you very much.
I hope you can hear the applause, Aimee. Thanks a lot for this presentation, stressing the urgency also of climate change. Are there any questions for Aimee? I think everyone is stunned by your... Well, I have a question. Earlier today, I showed a few like hand-wavy images of how we are going to look at sea level change in relation to subsidence, and I'll show later on the work of Aimee that you also know. How could you envisage that we use those IPCC global projections with perhaps local information? Would you have any models or data that you can envisage using there?
Yeah, so I think through this NASA Sea Level Explorer, you can download the total sea level change and the vertical land motion that the IPCC provided. So you can subtract the IPCC vertical land motion and replace it by your own vertical land motion. So you can have a way better locally based information. So you could, for instance, also use the groundwater estimates from Jenny and replace the AR6, the IPCC groundwater estimates, by your own local estimates. So I think in that sense it's quite powerful, but to start from the global or the regional sea level projections from the IPCC and then replace whatever you know from a local situation to really tailor it to the local circumstances. Because of course, with the IPCC, we're always bound to the information that is available globally, and that is a limit in if you want to really have a lot of detail on a local scale.
Yeah, thanks. And then I was also hoping you would say that you would have a local model for the Gulf of Thailand, but that I think is still
we can make that.
I was thinking. And then with the observations that
exactly.
people have
That's another thing you could do to improve the local situation, is to have a high resolution model for the region and feed it at the boundaries by the climate model projections, and then have a high resolution idea of the ocean dynamics in the region. Definitely, yeah.
Yeah, I think that would make for a nice new proposal.
Yeah.
But thanks again to Aimee. We're now switching to another online presenter, actually two presenters. We have Philip Minderhout and Isabel Kuijn. Can we get them? And thanks, Aimee, I'm waving to you.